In a previous video, we talked about what it means to be an acid or what it means to be a base by the Arrhenius definition and the Bronsted-Lowry definition and the Lewis definition. And for the purpose of simplification, let's just say down here for acids, we're looking at some amount of H plus, right? And that's the same thing as H3O plus in an aqueous solution. And I had mentioned previously this and this I will use interchangeably. And for basic solutions, we tend to look at the concentration of hydroxide ions, the amount of hydroxide we have. And the reality is we don't have to look at one or the other, because from a previous video we saw that there is a relationship between them, and it's kind of an important relationship. So it's an inverse proportion, but we know from a previous video Kw is concentration H3O plus times the concentration of OH minus. And we went on to specify that at 25 degrees Celsius, Kw is 10 to the minus 14th. So there's a lot of assumption that things are done at 25 degrees Celsius to simplify the math. Now, if you know Kw, and you know either H3O plus or OH minus, you know both of them, right? Because you can just rearrange this equation. So we can use either of these things, the OH or the H plus, to describe our solution. So with this understanding in place, the question comes up, why don't we just describe our solution by the concentration of H3O plus and by the concentration of OH minus? In fact, let's ask that question. Why not? Why not just describe the solution using some concentration of H plus or H3O plus or our concentration of OH minus? And there's a pretty important reason for that, and that reason is our range of numbers. Okay, so we have this huge range of numbers. For instance, you might be dealing with concentrations that are in the range of maybe 10 to the minus 15th molar up to 10 to the 5th molar or higher. You can have lower concentrations, you can have higher concentrations, but the idea is there's this huge spread and we need some way to deal with that. Luckily, math has given us the ability to deal with that, and that is logarithmic operations. And so we come up with this idea of a pH, right? Which is literally the power of hydrogen. We're talking about exponential values here, at which point it becomes readily apparent that this should have been 15 molar. 10 to the 5th molar is probably a bit unrealistic, but 15 molar is pretty reasonable. So once again, our spread there, 10 to the minus 15th to 15, not 10 to the 15th. Anyway, we left off with that power of hydrogen, and we're dealing with some log scale of hydrogen ion concentration. In this case, we'll be using a log base 10 scale of our concentration of hydrogen ions, right, or H3O plus. And that is where we get our definition from, and I'll write it two different ways. The strict definition you might see is that pH is defined as, so when you see a triple equals sign, that's general notation for is defined as the negative log of our concentration H plus, right? And that is the same thing as saying that pH is the negative log concentration H3O plus, all right? So that is going to be one of our primary equations that we're working with. Now, using your knowledge of logarithmic expressions, we can undo this, and this is log base 10 in this case, and say 10 to the negative pH will get us a concentration of H plus or H3O plus. All right, and that is another one of our important equations right here. I do want to mention, before I forget, that this negative sign right here means that as concentrations go up, the pH will go down, okay? So this thing right here, we'll put as fine print over here, as the concentration of H plus increases, the pH decreases, right? Therefore, lower pH corresponds with higher concentration of H3O plus. All right, and that is because, once again, of that negative sign there. Now, pH, power of hydrogen, isn't the only thing we can have. In fact, if we looked up here, we can also have something to do with hydroxides. And there is an analogous equation. You can say that POH, the power of hydroxides, just this exponential equation, negative log, again base 10, concentration of OH minus. And we can undo that, 10 to the negative POH, and in that case we're going to get the concentration of OH minus. And I'm going to sneak in here one other important equation, and that is that pH plus POH will equal pKW. Those are our key equations that we're working with here. In fact, let me denote that. If you're taking notes, make sure that this part right here is jumping out of the page at you, because those are the equations you're going to use. And while I'm saying this pH plus POH equals pKW, I do want to point out that very often for simplification purposes in calculations, you may see that at 25 degrees Celsius, pH plus POH equals 14, because KW is 10 to the minus 14th. And so this ends up being kind of a shortcut for things done at 25 degrees Celsius. Now, with the advent of a new type of operation, these exponential operations, I want to talk about a new sig fig rule for us. So we have this log, an exponent. Sig figs. And all it is that the number, an easy way to remember it anyway, is that the number of sig figs in the concentration is equal to the number of decimal places in the pH. So your number of sig figs in the concentration will be equal to the number of decimal places in the pH. Okay? So let me highlight those because I think it's kind of important. Sig figs for the concentration, decimal places in the pH. And I can kind of give you an example of how that works. First, we'll look at a situation where we're given a concentration of H3O+. So we'll say given a concentration of H3O+, and we'll say 1.00 times 10 to the minus 7th molar. And we want to find the pH. And we know our equations, write it out, use it as a checklist, whatever. We know that pH is the negative log concentration of H3O+, which in this case is the negative log 1.00 times 10 to the minus 7th, which in this case is 7.000. And I'm going to let that dry before I go back and highlight it. And our second example here, let's say you're given a pH of 1.00, we can turn that into a concentration, well, I guess we'd say find concentration H3O+. So that is our goal. Our pH then, our concentration H3O+ then can be calculated as 10 to the minus pH. If you hear clomping in the background, that's my kids running up and down the stairs, which is a bit frustrating. 10 to the negative 1.00. It's also very distracting, which is 0.10 molar H3O+. All right, now let's jump back there where hopefully my ink is dried enough. We have in our concentration 1, 2, 3 sig figs. And that matches with our 1, 2, 3 decimal places in the pH. Similarly, right here, we have 1, 2 decimal places in the pH and 1, 2 sig figs in our concentration. And maybe I can underline those in red. Those are our total, and this is our decimal places. And this is our sig figs in the concentration, and this is the decimal places in the pH. And I know that's cramped in there, but we'll have to make do. So this is what you're looking for, the number of sig figs in the concentration, number of decimal places in the pH. And just as a quick side note, people often ask why that is, and my explanation, whether it's true or not, if you have a number like, if I'm just going to point at this one here, if you had a number like 10 to the 1, that is 10, that's exact. But if you have a number like 10 to the 0.34, that is not exact. So the reason we care about decimal places in the pH is because that's the inexact part of the power. So the decimal places, well, the integer powers are exact, and the decimals are where our error is. So that's why we're looking at this part right here and this part right here.